All right, so with solving differential equations, first of all, they're going to give you a derivative formula written out. It's going to be written in dy over dx format. And then they're going to give you a point. Now, what that point is for is to help you calculate C. And what the formula is for is so that you can split it into one side's dy and one side's dx and integrate, because to solve a differential function means to integrate it back to the original function. Does that make sense so far? Okay. So we're going to integrate dy, and we're going to integrate. Okay, let's talk about this side over here. We're in a logarithm chapter, so we assume that the bottom is u and the top is du, right? Until we find a problem that don't fit that, which we did find quite a few on Friday that didn't fit that. So what's the derivative of the bottom? Okay, well, I got a 3 on top. Let me take that 3 off. So if I put -1 up there, that wasn't there originally, right? So what do I need to put in front? Yep. Does everybody see why I took the 3 off? It had nothing to do with the integration, right? You can take numbers out that have nothing to do with your integration. Then we realized the bottom was u, so we looked at what's du, and du had to be -1, so we had to put a negative out here to take and compensate for putting the -1 in that wasn't there. Now we integrate. So this becomes y. This becomes ln. Because when u is on the bottom and du's on the top, it becomes ln with absolute value bars on it. That's what we learned on Friday. Is every time you make it right to where u's on the bottom and du's on the top, we always throw du away. Even when we do chain rule, we never use du after we got it, right? So we always throw du away and make it an ln of the bottom. Now, what makes this different from Friday is I have that point. And so I'm supposed to plug that point in here to calculate our C. And so 0 is y, and ln of 2 minus 1 would be the x part. Well, 2 minus 1 is ln of 1, right? What's ln of 1?
Oh, 0? No.
That's right.
Oh.
And why it's 0, again, remember, ln is the inverse of e. So you're thinking about what exponent would e have to have on it for the answer to come out 1. Well, the only exponent that makes 1 is 0. And so therefore, the whole answer to this problem, since that part is 0, is 0. And so our final answer to the question is y equals ln of 2 minus x without the c on the end, because we don't need it. Look. Now, be careful. A lot of students look at this question and think, oh, well, the point was 0, so it was going to be 0, but that's not why. It actually calculated to 0, because it could have been something else. I kind of wish they had put a number over there in that point that wasn't 0, because that would have made it a little bit easier to see that it can be quite a few different things. Now, how do y'all feel about that so far?
So far.
Okay.
Okay. What?
Well, did you find my error yet?
Your error?
Mm-hmm. Well, this is the common error most students made, so that's why I made it.
Oh, I was going to ask you about that, actually, because I was like, wait, I'm just not going to say anything.
You have to remember that if you take it out, it goes on the ln. In front of the ln at that. Now, sometimes we take that back to a power problem. And sometimes we don't. So in this case, I don't think that would be a really good idea to try to take it back to a power problem, because it would be to the -3rd power, and that would make it division, and that would just make the problem look harder than it looks now. Does that make sense? But does everybody understand that if I put this back up as a -3rd power, that'd make this whole thing go down and be 1 over that to the 3rd power?
Yeah.
And you might see that as an answer sometimes. But be careful, if you take something out in front of your integration, don't forget to put it in front of your LN, because that is the most common error made in integration. All right, do you feel like you need another one of these, or do you think one of these is fine?
I think I'm okay.
What about you, Autumn? Well, you hadn't seen enough integration to know what you know. But there's plenty of other examples. But do you feel like you understand the part about solving for C? Because that's all this formula was for. Okay. Well, then we're going to look at evaluating first fundamental theorem of calculus, and that way you'll get better chance to see just regular integration.
Does it always equal to ln of 1? Because then, like, what happens if it's like ln of, like, 2?
Oh, well, that's a good point. What if it was ln of 2? Well, if it was ln of 2, then you move it to the other side, and C would be an expression.
All right.
Yeah, that's a good point.
So I
If this isn't ln of...
ln of 2.
Uh-huh. Right, yeah. Oh, in this case, let's pretend for just a minute that, well, I'll tell you what, let's do that. Let's make a second point for the same question. Okay? What if our point was 3, 2? We'll just solve a second point instead of doing a second question. All right, so we're going to plug in 3, 2 in our formula. So 2 equals negative 3 ln of, oh, wait a minute. I went the wrong way with my x value.
I was going to say, doesn't that make sense?
Yes, we can't go that direction. Let me do 1, 2. 2 minus 1 plus C. Nope, I did the wrong thing. Why could I not do it right?
4?
0.
0.
Let's do 0. I'm trying to do a number that the math's easy and it won't mess me up. All right, so we're doing 0, 2. So I put in 0 for x and 2 for y, because you can have any numbers. You just, and I could have done it with the negative value, but I was trying to stay away from negatives. All right, so you're asking me what happens when I do this and I get ln of 2, because 2 minus 0 is 2 and the absolute value is 2. And you're saying, well, what do I do then? Well, I move it to the other side. And that whole thing is C. Does that make sense so far?
Yeah.
And if you get an expression like that that's C, then what are you going to do about that with your original function that you're putting it on the end of, right? Well, no, let's see. Y equals negative 3 ln of 2 minus x plus 2 plus 3 ln of 2. Well, that looks rather nasty. Can we condense? Might make it better. Might not. But it might be something they would do.
I just didn't know, like, what would you condense?
The 2 ln's. Let's look at that. What if we had 3 ln of 2 first minus 3 ln of 2 minus x? That plus 2 is just going to stay out there because he's a constant, okay?
So, like, they just changed it to make it look a little bit neater.
Well, not exactly. I think we can put some of it together. We're going to try. If we can't, we're going to leave it like that, okay? Because it is possible that if you get a value that keeps the ln, they want you to condense it. Now, I didn't put the negative 3 into the power and do all that kind of condensing because that would have made that problem look worse. But in this problem, condensing might make it look better. For example, if I put this 3 back up here, won't that just be ln of 8? Everybody agree? And if I put this 3 back up here, then wouldn't that make that division?
Yeah.
Over 2 minus x absolute value to the third power plus 2. And why did I leave the absolute value bars instead of turning them into parentheses? Is because I still don't want it to be negative. Well, that looks better than some respects, maybe not a whole lot better, but it does look some better. Because now I see a clear constant. Does that make sense?
Yeah.
But I don't know that it's any better in terms of,
It looks neater, but essentially.
it looks neater, but all of this is the constant. So by doing this, we don't see the clear constant that the original problem gave out. We just see part of it,
Yeah.
but it looks a little neater. So I think that's why a lot of times they'll give you values that ln of 1 ends up coming out of it because it does the math so much quicker, but it doesn't have to be ln of 1 every time.
I was just making sure, because like, I figured like in the homework at one point.
Yeah, it might not have ln of 1 every time, right. All right, well now we're going to look at just regular first fundamental theorem of calculus, and this will give Autumn just a few examples of just integration. But maybe some of them won't be ln, so she can see some of those as well. So we're going to do definite integral, which means the first fundamental theorem of calculus. But as we go through these, each one of them is going to have something really specific with our u du work. And again, it may not all be ln. We'll see. Because as we saw in the homework that we probably were working, they weren't all ln. The notes weren't all ln. I'm sure the homework wasn't. All right. So with integrating from 0 to 4, 5 over 3x plus 1, if the bottom is u, what would the top have to be?
3.
Okay. Then I'm going to take that 5 out and put a 3 up there. Now, if I put a 3 up there, what does that put in front of my problem? Okay, well, I'll put it underneath the 5 and make it 5/3 then, because 1/3 times 5 is 5/3. So if you need a whole number on top, just put it underneath one in front if you've got one in front. So that makes this du and u now, right? We've cleaned up the problem. We've made the bottom u, the top's du. So we're good to go. Now here's where you get some options. You can put 5/3 in front of the whole problem and don't work with it until you're done with the first fundamental theorem of calculus. Or you can put 5/3 on each one of your f of b minus f of a work. Does that make sense? I don't like putting it on each myself because I just think that makes it a little bit more complicated. So I always keep my 5/3 out here, but now if you want to put it on each one, you're welcome to. Always put ln at the bottom because that was u. Always put it in absolute value bars unless it can't be negative. And since linear can be negative, we don't want to leave off those absolute value bars. So now we're going to evaluate by putting 4 and 0 in and get our numbers, and then we'll multiply it by 5/3. So that's the new part for today's lesson. Up until this part, this would have been our lesson on Friday, and you would have said this formula plus c for the indefinite integration. Now we have numbers to plug in, so that's the only thing that's making today's lesson different. So what will the ln on the first one come out to be?
13.
Okay, and the second one? Our favorite number, 1,
Oh.
right? And ln of 1 is 0, so the answer to this problem is 5/3 ln of 13. Now sometimes they might ask you to give a decimal answer. Sometimes they want it exact. They would not ask for both on the same question. So in a multiple choice situation where you're taking your AP test, you would need to look at it and decide, you know, am I looking for decimals because I'm on the calculated portion of the test, or I'm looking for that because I'm on the non-calculated portion of the test. It's not hard to type that in the calculator and get an answer, but the key is you need to know which way they're going. And sometimes it's not clear in our homework which way they're going. So how about we write both every time, maybe? I'll just tell you the decimal for this one. 4.275 would be the decimal if I type 5/3 ln of 13 in my calculator. All right. So what was one of our clues that we talked about on Friday to help her with some of the clues that we looked at, that we know this is LN before we even started?
The bottom is bigger than the top, like exponent wise.
Yes, that was one of our clues. If the bottom power is bigger than the top, and actually it has to be a difference of 1. If the bottom power is cubed and the top power is squared, that's a difference of 1. This was power of 1, power of 0, so it's a difference of 1. The bottom has to be 1 more than the power on the top. Then it's got a chance of being LN. Otherwise, we got to look for something totally different. So as we go through these questions, we're going to keep trying to look for that kind of thought. Not every problem fits that thought, but quite a few will. Another thing we looked for on Friday was not only did we compare powers, but we also found out that once in a while the problem looks like chain rule. Would you agree?
Like right now.
Yep, like right now. So that's the other thing you can look for. If your LN's on the inside of something, then 9 times out of 10, you need to separate your problem out because your U is in the wrong place for your DU type work. For example, 1 plus ln of x squared is the problem. This x down here is the derivative of the inside.
Don't have to like flip it though.
No, because it's on the bottom. So if I want to move it over here and put it on the bottom like this, I'm just separating it off. The derivative of 1 is 0, right? The derivative of ln is 1 over x. If you multiply 1 over x times this, it puts the x on the bottom. So let's take it back off.
I was talking about like you like just a second ago you was talking about the power thing.
Oh, but I can't do that on this one because ln's not by itself.
Oh.
It's on the inside. See, if you got an ln in the problem, you know good and well that you're going to be taking the derivative of that, okay? So keep in mind, the power rule can't be used if you see the word ln. It has to be changeable if you see the word ln. See, in the previous problem, there was no ln in the original problem, so that's why we're using the power rule.
Oh, okay.
See the difference?
Yeah.
Yeah. So in this problem, I see ln, so I know the derivative ln has to be somewhere in there, and that's what that x on the bottom's for. So now we're going to integrate u squared du. And notice I dropped those numbers for a few minutes because, remember, I can change them to u if I want to, or I can just do the integration and then put the numbers back on it. So this is going to become u cubed over 3. Everybody agree? So that's going to be 1 plus ln of x to the 3rd power over 3, and we're going to evaluate that from 1 to e. Now you're going to say, wait a minute, they're evaluating that with a letter. Is that the second fundamental theorem of calculus?
Yes.
No.
No.
If it was, I'd have just plugged the e in and wouldn't have done any math. This is not the second fundamental theorem of calculus because e's a number.
Yeah.
Remember, yeah, it's like pi, it's a number. So we're going to treat it that way. So we're going to do 1 plus ln of e to the 3rd power over 3 minus 1 plus ln of 1 to the 3rd power over 3. Does that make sense to everybody on how I plugged in the first fundamental theorem of calculus?
Yeah.
So what do e and ln do? I mean, how am I going to evaluate e and ln? Well, they're on the same button on the calculator for a reason.
Yeah, I was going to say they're similar for something. Do
They like cancel out or something.
They do. They cancel out. The thing is, you got to know what they cancel out and do.
Ooh.
So e is to the 1st power. And when e and ln cancel out, it gives you 1.
Okay. So when they cancel, they give you 1.
Mm-hmm. Now, if it had been e squared, if I had ln of e squared, it would be 2.
Oh, so whatever power E's at, that's what it equals up.
Exactly. Whatever power E has, that is the answer to the question. So because of that, that's why you have to understand that there's a power on E. So this becomes 2 to the third, which is 8/3. Now over here, ln of 1 is 0, so that makes 1/3 when you cube it. So the answer to this question is 7/3. And in that particular case, we probably would not write a decimal answer because it's repeating and it doesn't have an ln on it or anything. That other one, we wrote a decimal answer and the exact answer so we could see what 5/3 ln of 13 kind of looked like. This clearly, I can tell what that looks like. I mean, that's just 2 1/3.
If we get an answer, like an actual like number instead of like ln to something,
Mhm.
would you just keep it to like that number?
Yeah, I usually do. Unless they tell me they want a decimal answer. I would leave it this. The other one I turned to a decimal just so we could approximate and see what it kind of looked like. And not every time do you do that either. Sometimes you just leave it ln. All right, let's look at another example and see which one of these two it kind of follows. Do we need to look at powers or do we need to look at chain rule? Because that's two of the big things that we have discussed today that we discussed on Friday as well. So I don't see an ln in this problem, so does that mean it's not chain rule?
Well, it could.
Well, okay, let me rephrase that. When I mean chain rule, I mean U really is inside of something. Do you see a U inside of something? No. Okay, second of all, our second thing we talked about today is the power on the bottom has to be 1 more than the power on the top for it to be ln. Is it ln?
No.
No. So what was our third thing that we discussed on Friday that everybody goes, about? Long division. When the power on the top is higher, we know we have horizontal asymptotes, when we got equal to and less than. And when the power on the top is higher, we know that we don't have a horizontal asymptote. Well, that's because you can divide the problem out. So we have to be able to do long division. So let's go back and let's review long division with this problem one more time. The bottom goes on the outside, so you have x plus 1. It's going to go into x squared, no linear, so I'm going to put a 0 for linear, minus 2. Does that make sense so far? If it don't make sense, you'll see real quick if you forget to put that 0x in there, what happens. It won't line up term-wise, and then you'll realize, oh gosh, I should have done something about that. But that's what you got to do. You got to make sure all your terms on the inside are filled in. Don't care about, let me phrase that. If you're missing a term in the middle of your polynomial, you always fill it in. Don't ever add something to the front. But if you're missing something in the middle or you're missing the constant on the end, you would want to add something to it. So now, how many times does x go into x squared? It means how many more x's do I need to turn it into squared?
X.
1 more x. All right. Now, according to division, that's what you do first. You try to figure out how many times it goes. And then you multiply what you've written on top times the front and put it underneath. So x times x is x squared, and x times 1 is 1. But then in division, you're supposed to multiply and subtract, right? So we're supposed to change the signs and add. The quadratics drop out. I get a negative 1x. I bring down one term. For every term that drops out, I get to bring another column down. Well, only one dropped out, so I bring the other one down, which is good because I only had one thing to bring down anyway. Now, what does this x need to turn into negative 1x?
Negative.
Yeah. So we're going to say subtract from 1 and multiply by negative 1. Negative 1 times that makes negative 1x. Negative 1 times 1 makes negative 1. But again, remember.
I'm probably going to have to go over how you did this because for some reason the negative 1x and then the plus 1 or the minus 1, I'll get confused. Is it because it's x plus 1 in there?
I'm not with you where you're at, sweetie, so let me go back. All right, so first I figured out it went x times. And I did x times x is x squared and changed the sign to a negative because it has to be the opposite because we're supposed to be subtracting. And then I did x times 1 is negative 1x because I made it the opposite because these have to be the opposite of what you get from multiplying.
Okay, I get the x, I just forgot there was a plus 1, and so when you keep, like, when you did the minus 1x, because what's going on?
Yeah, I have to change all the signs, and I just did this one in color so it'd be more obvious. See, the first time I did it like this. Okay, so you always change the signs before you add because you can't subtract. Polynomials, we only know how to add. And that makes this drop off and give me negative 1 as my remainder. Now, what you do with that remainder is really important because that's what's going to set up that last piece of the problem. You're going to take the remainder and put it over the divisor. Now, this may look like this is really, really hard, but if you don't do this, you can't integrate this problem. You've got to be able to divide. Because now I have some easy pieces to do, and I have a fraction I think we can do. This fraction we couldn't do, but that fraction over there has got a higher power on the bottom than the top by 1. Right? So we should be able to integrate it. Now, so we're going to go back, and we're going to set up our problem with our new math. Now, each piece, you got to think about them separately, y'all. You can't think about them in relation to the others. So the first piece is 1x, linear. What does linear become when you integrate? Squared. So we're going to put a square over 2. Or you can say 1/2 x squared if you'd rather. What does a constant become when you integrate? A linear. So I'm just going to put an x on him. Is everybody okay with that?
Yeah.
All right. Now, let's look at this fraction. Well, it's going to have a minus sign, obviously, right? But isn't this u, and the derivative of that is du on the top? X plus 1, if it was u, the derivative of that is 1. The whole thing is 1. So wouldn't that mean that's ln?
Yeah.
So we have ln of x plus 1. And we're going to evaluate that from 0 to 2. All right. So 2 squared over 2 minus 1 times 2 minus ln of 2 plus 1 minus. When you plug 0 into that, that's 0. When you plug 0 into that, that's 0. Is 0 going to be the answer to this one too? Because ln of 1. So at least we don't.
ln of 1.
Well, if you plug 0 in, 0 plus 1 is 1.
Because ln of 1 is 0.
No, I mean, you have 2 plus 1 right there.
No, I'm talking about plugging in the second number in.
I was like,
Yeah.
2 plus 1. I'm like, that's 3.
What I'm getting at here is that I don't need to write the second one down because they're all 0.
Okay, yeah, I'm sorry.
Okay, you're all right. So I put 2 in because I know I got to work the 2's. But 0 came out 0 in each one of them, so I just wrote minus 0 to save time. So this one's going to be 4 divided by 2 is 2, and this is going to be minus 2. Well, that canceled out. Yep. Negative ln of 3. And we can drop the absolute value bars because 3 is positive. Now that, again, could be a problem. They might want a decimal or they might want the exact. But I'm going to leave it exact because I know y'all can type and get decimals. All right. Last question we're going to look at is for this section is trig. And it should be something we can integrate fairly easily. Although on Friday we did notice that sometimes we have to work a little harder at it. But I don't think we do on this one. Is somebody at the door?
Oh, no, that was me. I'm sorry.
Oh, it's okay. I just want to make sure I didn't hear somebody knocking at the door. All right. Do you think the derivative of u on the bottom is on the top?
Yes.
Is it all good? Every little piece?
I think
I don't need anything? Okay, so theta becomes 1 and sine becomes cosine, and I don't need to add an extra negative because it started with an S, right? Okay, then we got u here and we've got du here, so we're good. This is ln of theta minus sine of theta evaluated from 1 to 2, which is not trig functions, which means that we're probably not going to get the same kind of answer for this as if they put trig numbers in there that we actually know the answer to. Kind of would have been nice if they'd used some trig functions once in a while with pi's. So we're going to put in 2. Whoop. Minus, we're going to put in 1. Do you see why I say we don't know the answers to the signs? Because 2 and 1 are not angles we're used to, especially in radians. Can I make it look better?
I feel like you could, well, if you,
Put it in
Don't mind.
division.
Put it in a division? Okay. So like 2 minus sine of 2 over 1 minus sine of 1. You feel like that makes it look better because it's not so stretched out, which is correct.
yeah.
And then if they wanted a decimal answer, you could just type that in your calculator and get one, and I'm going to give 1 on this one because I did notice that they did that sometimes in the book when the problem had a lot of stuff inside the absolute value bars. They wanted to give a decimal answer.
Like say when you do that,
Mm-hmm.
you plug that in your calculator, do you have to put the absolute value bars in the like LN?
Well, you might have to because we don't know what this subtraction is going to give. But you could try it without them first and see if it'll give you an answer. It won't give you an answer if it's not supposed to, because if the inside of this comes out negative, ln will be an error. And then you'll know to go back and put the absolute value bars on. All right, the next section of questions that we're going to look at, they're kind of interesting. You know how sometimes y'all are working a problem, I said y'all should have gone further?
Yeah.
And you didn't realize you should have gone further because it was trig? Well, that's kind of what these questions are going to kind of show us, that you could integrate a problem and get 2 different answers, but one of them might be better than the other one because they're equivalent. So, the directions for this set say show that the 2 formulas, oh, there's not a 9, that's a U.
Huh? That's what I know.
You could get it beside that if you wanted to.
Yeah, I was gonna put it right here.
You probably could get both, or at least one of these beside it, I know. Because, I mean, I spaced it way out and took a half a page, so I know you can get one of them there. So if you want to put one of them there, you can put one there and then go to the next page because the other one's longer.
I'd rather just put this first.
Okay, go ahead.
I think it's good.
Are equivalent. So we have 2 integration problems. One said somebody did tangent of x dx and got negative ln of the cosine of x plus c, which I think is actually the formula on your formula sheet that we talked about on Friday. For your information on them, what we found out was we knew how to integrate sine and cosine words here, and we knew secant squared's tangent and cosecant squared's cotangent and stuff like that. But when we had the plain tangent word, we didn't know how to integrate it, but there were formulas on our formula sheet that showed that. And this is one of them. That when you do tangent, it comes out negative ln of cosine of x plus c, which I told them there are 4 of those and they need to memorize. But someone worked their ln out themselves and they got this. ln of secant of x plus c. Our job is going to be to try to show the math that proves that these 2 are equivalent. that this formula, that the formula sheet gives is the correct answer just as much as the secant is. Of course, the formula is better, but it's not wrong that somebody wrote secant of x. They just didn't go far enough. Kind of like y'all don't go far enough sometimes on your trig. So we're going to start with the second formula and try to show it how it turns into the first formula. Since, if you remember, well, I don't know what you remember about this in pre-calc, but we do problems in pre-calc in which we're all the time trying to do trig substitution to make the formula more simplified. Well, you'd think this would be more simplified, but more simplified trig always has the word sine and cosine in it. So you want to start with the one that doesn't have sine and cosine in it and turn it into the one that does. Does that make sense to y'all?
Yeah.
Okay. So step number 1, our given. Know how you always start with given? Now, it technically does not matter which one you start with, but I'm going to tell you on this one it does. You have got to start with this one because it doesn't have the word sine or cosine in it. Now, what is secant?
Like 1 over.
Right. So we're going to turn it to a word, well, not theta. We're going to turn it to a word that has sine or cosine in it by substituting it in a trig for it. Then we're going to expand and see what happens, because we ended up with a division problem. So it's ln of 1 minus ln of cosine of x plus c. I didn't put those absolute value bars in the right place. Hold on. It should be on the whole problem. I wasn't paying attention. I don't have to put it on the ln of 1 part because 1's not negative. But I do have to put it on the cosine because cosine might be negative. And then, what's the ln of 1? 0. Now this is a proof, so I have to actually show the 0 plugged in. And then I can drop the 0, and doesn't this look like the real formula? So if you were working a problem that came out secant, you would want to be able to know how to convert it to words like sine or cosine. Now, not every time would that need to be done, but, I mean, it could be. Now, I have one more of these, and it's for one of the other two formulas. And just to try to help you to learn the formulas, we found out that tangent is sine over cosine, right? Remember that formula, sine over cosine? Autumn, you with me? Okay. So, well, we found out there was a pattern to the formulas, that the bottom of this original problem always ends up over here, and the reason there's a negative out there is because that starts with a C. If I was doing cotangent, then it would be, I'm not sure about the negative, I've got to go back and think about that. But this word is cosine over sine. Somebody look that formula up for me and tell me if it's got that negative. I don't think it does, but I can't remember. Does it?
Cotangent, it's just sine.
That's what I thought. As soon as I wrote it, I knew it sounded wrong. All right. Isn't the bottom of this word sine? So that means it's ln of sine. And I don't have a negative on it because sine doesn't start with a C. So in these two problems, when you integrate them, they integrate to the word that would have been on the bottom of the trig that you substituted. Does that make sense? My second example is for secant and cosecant. So we'll get to see a word association with that, as well as we're going to get to see a trig problem. All right, so for number 2, we're going to do secant, and then at the end we'll talk about that relationship of how can you remember the formula. All right, so it's ln of secant of x plus tangent of x plus c. I think that's the original problem. And then, but I'm not positive, but I think it is. And we're comparing it to this one, which I think is not the original problem. Now, sometimes I have trouble deciding which one I want to start with because it really doesn't matter which one you want to start with. And I'm going to tell you, sometimes I do the one's a different word because I want to change it all sine cosine, but this one didn't change it to all sine and cosine, did it? All it did was change a bunch of signs around. It looks like I got the answer. So I usually start with the one that's got the positives in it and try to figure out how they got those negatives. Does that make sense? Because that would be a simpler problem to start with, which is actually the original rule, I believe. The original rule is the first one. So we're going to start with that, and we're going to try to see how do we turn that into the one with the negative on the outside and the subtraction sign. Now, for you to know the rule, tell them how to remember these, Autumn, what I told them about this one is secant always deals with secant tangent. But when we thought of it before, the derivative of secant was secant tangent multiplied, right? So if you want to integrate secant, it becomes an adding problem because that's what logarithms change multiplying to adding, remember? So if you're integrating secant, remember secant and tangent always go together, but it's kind of like it's been expanded. So multiplying became adding in the integration instead of it staying multiplying like it is in derivatives. And same thing with cosecant. Isn't cosecant's derivative cosecant cotangent multiplied? So if you're integrating cosecant, it becomes ln of cosecant and cotangent added or subtracted. I'm not sure. I can't remember off the top of my head. But it helps you to remember the relationship. And I think there'd be a negative on that one. Because I don't think the reason there's no negatives on this original problem is because it doesn't have any C's in it. So we learned 4 new formulas for integration on Friday about trig. And you just got to come up with some way to help you to memorize it. But I thought this one was easier to memorize because we know secant's secant tangent. We just got to remember to put plus to expand it for logarithms type thought, and it'll work. All right. This one's worked a little differently. It does not help to change, well, I guess it could help, but it's not going to, I don't think. I don't think it helps to turn this to 1 over sine and sine over cosine. I don't think that helps at all with this question because the answers don't have any sines and cosines in it in the other part. So we got to come up with a totally different way to work this question than the last one, and that's what makes these kind of hard sometimes because they're not all worked with the same kind of trig thought. But if you see different words, like you had a word that means sine or cosine in it, then that's probably why you want to turn to that. But here I don't see different words. I see different signs on the same words. That makes me think conjugates. Don't know if it makes you think conjugates, but when I see something change from an addition problem to a subtraction problem, that makes me think they're using food line. And that's exactly what they did, is they tried to use food line to help do this question. So, now, let me explain why I'm using food line. Number 1, when you condense problems sometimes, or even if you're just working a question, the only way there's going to be a subtraction sign right here is because you had something that was division that you turned into subtraction. Does that make sense? Because I don't have any C words. There's no way to get that negative. I have no C words to put a negative in front. So the only way I'm going to get it is from division. And so I had to think of something I could multiply the top and the bottom by that would give me that on the bottom. Does that make sense? So that's a clue. Opposite signs is a clue that food line will help you if you get a common denominator, so that this subtract this would come from the bottom here. Now, once you realize you need those opposite signs, once you realize that the top one is plus and the bottom one is minus, and that the only way you can get this subtraction sign here is from changing division to subtraction, then you've got to put the same thing on top and bottom, because that keeps it an equivalent fraction. And we can food line the top out because we can stick a 1 under this. And hopefully maybe some kind of trig will happen with that we can get rid of that part, because we don't want that part. We just want the division. So secant times secant is secant squared, and tangent times tangent is tangent squared, and negative times positive is negative. And that way we end up with what we want on the bottom. Now, we didn't get what we want on top, because I don't want a top. I got to figure out how to get rid of that top. But we've got what we want on the bottom, so this division can change to that subtraction now. Does that make sense so far? So big thing you have to remember is when you haven't changed words at all, but only signs, you have to use food line to make the signs change. So now, at this point, we've got to come up with, what does secant squared minus tangent squared make? Now, you may not remember this, but there is a rule for the Pythagorean that says secant squared of x equals tangent squared of x plus 1. That's a Pythagorean triple that we talked about for trig. And if you take the tangent to the other side and subtract it to make it look like the top of this problem, then it's telling me those two things subtracted make 1, and now I've got something to substitute in on the top. So anytime you see stuff about squared, go look for a Pythagorean identity off of your formula sheet that has the unit circle on it. So now I have ln of 1 over secant of x minus tangent of x. Do you see where I'm going with this in the expansion? Why I thought expansion might be important? Because what's ln of 1?
0.
There you go.
It could be negative 1 when you move that 1. Now you move the tangent over, just kidding.
Yeah. So I have ln of 1 minus ln of secant of x tangent of x plus c, because we're just keeping up with that plus c all the time. So the ln of 1 can be plugged in as 0 minus ln of secant of x minus tangent of x. And then I'm to my original problem that I wanted. So those are the two big trig things you can do. If you see they change the words to sine or cosine, then you want to start with the one that doesn't have sine or cosine in it. If you see you have adding and subtracting problems changing signs with trig, then that's a big clue that it's food line. And that way you can multiply by the food line pattern on top and bottom, and hopefully you'll be able to use one of those Pythagorean identities. This also works really good for secant and cosecant and cotangent as well. So this is the trickier part of our lesson. All right, the next thing we're going to look at is the second fundamental theorem of calculus. We're going to review that. It says to find f prime of x. Okay, they abbreviate the second fundamental theorem of calculus like this. So the question will be written, capital F of x equals the integration of 1 to x of 1 over t dt. And if you look at the integration problem, you can see definitely that t's derivative is sitting on top right now. We got that du thing going on all over there, right? U du. But this is the second fundamental theorem of calculus. So We could do the math out the long way, but I want to really start trying to focus on that short way, so we're only going to look at it short way this time. What we learned is if there's an x here, you plug it in for t. And if the derivative of that's not 1, you put it in front of it. What's the derivative of x? Okay, we're good. So the derivative of this problem, okay? Well, I don't want to write that over there. Let me write it underneath. The derivative of this problem, okay? I want you to keep in mind two things. When you integrate, it goes back to the original problem, right? And if you differentiate it, it goes back to what's inside of here. Everybody agree? So the differentiation of this is just 1 over x. Because that's all it's going to do. It's just going to plug that x value in. Because if you differentiate and integrate, you're back to the same place you started. You're just going to have a different letter in there.
It just looks like you plugged in x for t,
That's all it did.
basically.
That's the rule. That is the rule. Unfortunately, they're not always quite that short, but that's the concept of the rule, is you just take out the t and put in the x. But that's because the derivative is 1 that it looks that simple, so we're going to look at one more example of this. Because I don't want you to think that it's quite that short, but it is pretty short. And I didn't even change the problem that we're using. I just changed the stuff on the integration to make the math easier. So this second problem is still 1 over t. I still got u on the bottom and du on the top, but I got a lot more complicated stuff here. Does everybody see that? Okay. So now, we got to break this up. You can't have x in both places. So we want to integrate the x one separate from integrating the 3x one. Does everybody agree with that thought based on what we've done in the past?
So would you do the negative thing?
Well,
The negative to bring the x up, or not just...
yeah, we will do the negative thing, yes. But before I do the negative thing, we got to think of a number we can put here. Now, we always use 0 before. I can't use 0 on this one. Can somebody tell me why?
Because you gotta put it in the denominator.
I'll put it, yep. Whoop, I didn't mean to write 0. So I can't put it there because it'll make the denominator 0, so I just chose 1. I chose just another number that I could plug into it. And she's right about the x over here. We've got to turn that around so that the x is at the top, because the first fundamental theorem of calculus does not work unless it's at the top. So now this part of the problem looks like the last question. Would everybody agree?
Yeah.
So it's going to be minus 1 over x. But this part over here looks a little bit more complicated because the derivative of that's not 1.
What you just done.
It's like you put the 3x in, but you multiply it by the derivative. This is du, kind of that. Does that make sense?
Yeah.
So now I've got, well, 3 over 3 cancels out.
Does it make it 0?
Well, that whole problem is. That's because that's an odd function. 1 over t is an odd function. And half of it's above the x-axis and half of it's below the x-axis, and they're equal. Does that make sense? Remember how area below is negative and area above is positive?
Yeah.
So because half's above and half's below, it made them cancel out. All right. Now we're going to look at a different direction for 2 more questions, and then we'll be done, I think. Pretty sure that's right. Yep. So second fundamental theorem of calculus is really easy as long as you fill in the thing they give you for the variable and put the derivative of it times the problem. People forget to times by the derivative. It's why most people miss second fundamental theorem. All right. This question says to find the area, and I only have one of these because it's pretty simple. So it sounds like the directions we've seen before. Find the area of the region bounded by the graphs of the equations. And what they do, and this is actually question number 57 out of the book, so you can refer to it when you're doing your homework if you need to. They'll give you a y equal to or an f and an x equal to equation. They will tell you some other restrictions for your question. Now, you can graph it and look at it if it helps, but it's not an absolute that you need to graph it and look at it. It's just a possibility. This question is saying these 4 equations bound my region. Well, y equals 0 is the x-axis. So for that to bound my region, that means I have to either be all above it or all below it, or maybe half and half or something like that. From 1 to 4 sounds like I want to start on 1 and go to 4 and have a little piece in between here. Does that make sense so far? So being able to graph it could give you just the sense of, you know, how big a section am I talking about. So I'll just throw this in y equals real quick. Okay, x squared what?
Plus 4.
Over x? Okay. Alright, and I'm going to put in something else on this graph. So I'm going to quit that just for a minute. I don't know if I can do both of them at the same time. Well, I'll tell you what, let me do Zoom 6 first. Alright. I don't know if you know how to do this, so I thought I'd show this. If you go back to the home screen and you go second draw is the program button, you can draw a vertical line. I don't know if it'll,
Showed us this, but
I can't remember if it'll do 2 of them, so I'm going to try to do 2 of them. Okay, forgot to hit enter. Nope, it won't do but 1 at a time. But you can do 1 at a time. But I think it takes the other one off when I do the other one. So I'm going to see. All right, there's 1. Now if I quit, go back and do 4. Okay, good. Put them both on there. And the third line, y equals 0, is this line. So we're talking about this right in here. So if you had to estimate it, it's 1, 2, 3 across, 1, 2, 3, maybe 4 up. It's about 12
Yeah.
if it was straight. So I think it's going to be less than 12. Might be a little more than 12, depending on, you know, how you estimate it. Well, so I got a visual now. It's going to be in here. But since that's not a straight side, I can't use one of our geometry formulas to do it. So I set up the integration from 1 to 4 of x squared plus 4 over x dx. The 0 doesn't have anything to do with setting up the integration. The 0 had to do with the visual. Now, the power on the top is higher than the bottom. What do I need to do? Because it's supposed to be less.
Oh, you mean everything, never mind.
Yeah, I meant in the problem. 2 is higher than 1. The bottom's supposed to be 1 higher and the top's 1 higher. I have to divide. Well, at least this isn't long division. This is just divide by x. So that'll save us a little time. X goes into x squared, x times. X goes into 4, none, so I'll put my x back down there. So that's nice. It's a monomial. It's easier to divide monomials. You just put x under each one. And then we're going to integrate, actually we're going to integrate it. Okay, remember, x goes up by a power to 2 over 2. This is ln, because the derivative of x is 1, and I could have a 1 on the top because I could say this 4 is out here. Everybody agree?
Yeah.
So that's plus 4 ln of x, and we're going to evaluate that from 1 to 4. So first we're going to put in 4. And then we're going to subtract putting in 1. So this time we're going to actually have to put it in, because that whole side doesn't come out 0, does it? So we've got 16 divided by 2 is 8, plus 4 ln of 4. And 1 divided by 2 is a half, so we're going to take a half off. And ln of 1 drops off. So I don't know if we need to get a common denominator or just at least put the 8 and a half together, I guess. Let's see what that looks like. 8 minus a half is 15 halves. I guess we could leave it like that, or we could just get a decimal. Because otherwise you'd want to get a common denominator for both of them. I think it... No, that's... Where? That's 1 to the second power. I think I wrote a decimal answer on this one. 13.045 units squared. And you don't always have to put units on them. Sometimes you'll notice with the AP test they won't put units on it. Sometimes they might give you a unit in the word problem to know to put on it. So knowing it's units squared, so that if they say it's in centimeters, you'll know to put centimeters squared. And then the last question goes back and pulls something together from word problems that we need to know about profit, I think. It's about profit.
I learned about that in civics.
You did?
Yeah, they were talking about the marginal
Okay.
stuff and all that, about how much cost with 1 extra unit would it be worth
To make them more.
yeah, and I was like,
Alright, so this is related to number 63 that's in the book. And I'm not going to have you get your book, but I will pull mine out here and read it, what it says, because I don't remember what all my stuff in here meant. Okay. Alright, so the demand question for a product, little p, okay, demand, you know that funny little p, is 90,000 over 400, I think it says plus 3x. So that's our demand formula. The question says, find the average price, P, on the interval from 40 to 50. Okay? Find the average price from 40 to 50. So this problem is just slightly easier to work than it could have been because they didn't ask me for revenue, they didn't ask me for cost, and they didn't ask me for profit. They asked me for average price, and that is the price formula. So at least I don't have to convert it to like revenue or something else. So I'm going to be integrating it from 40 to 50. The price formula. What about this word average? What do you always put on your problem when you want to do an average? Yes. It's 1 over B minus A. So in this case, that would be 40 minus from 50. Everybody with me so far? So we've got our formula set up because the word average means to put this fraction of 1 over B minus A in front. It said to do it to the price, and this is the price formula. That's what demand is all about. What price are you going to set it at so that there'll be a lot of demand for it? Because if you set the price too low, you won't make any profit. Too high, nobody's going to buy. So this is 1/10. Now, does this 90,000 have anything to do with that? Well, let's take that 90,000 out and integrate it 40 to 50. Now, what does have something to do with the derivative for our U to U work?
put a 3 up top.
We need a 3 up top, so then I'm going to put a 3 down here in the bottom with 10. So now you can That looks like a 4 in front. Let me take that U off. Now we can integrate this with LN, and we've got this to put out front that we can deal with. We know it's going to be LN of 400 plus 3x, and that we're going to evaluate that from 40 to 50. And when we get done doing that, whatever this is, we're going to put in front. Well, 10 just drops to 0, so that makes it 9,000 divided by 3. So 3,000. Is that right? Okay. So we're going to evaluate that from 40 to 50, and then we're going to multiply it by 3,000. So ln of 400 plus 3 times 50 minus ln of 400 plus 3 times 40. Now this is where having a calculator would be very handy, because you could type all that in at one time, although we could do this little bit of this math and save a little bit on the calculator, because 3 times 50 is 150, and 150 plus that would be 550, and we don't even need the absolute value bars anymore because it's come out positive. And then that's 120 plus that would be 520. And if we condensed it, then it's just ln of 550 divided by 520, and a 0 could drop off, and we could just type 3,000 times ln of 55 over 52, if I've done the math right. Yeah, well, since you got your calculator out, I'm curious to see if that worked, because I didn't work it that way on my paper. I just thought about condensing more so that it would fit in the calculator better. I could have stopped way back up there. But
0.0561.
did you multiply by the 3,000 already? Okay, do times 3,000.
168.2684.
Round it off to 2 places because it's money.
27.
27. So each item would cost $168.27, whatever this item's about. It didn't tell us what we were buying, but that would be the average price. So from the time the first one was sold to the time we stopped selling them, so to speak, kind of thing here. Let me phrase that. That's not exactly true. From the time we sold the first 40 to the time we sold the first 50, the price would vary, because 40 is not that many, but it might be somewhere along there they've got back the R&D money and they might drop the price or something. So the price might be going up and down for different reasons during selling 40 items to 50 items. And so because of that, this evens out the price and say they sold it for $168.27 the whole time, when that's not really true. It might have been more than that at 40 and less than that at 50, or vice versa. So that's kind of where it goes. All right, so the homework for this is going to begin on page 327. I didn't sign 28 and 30 on Friday. I thought we stopped at 26, right? Okay, so we're going to do 28 and 30. That's 2 of those that's the differentials where you've got to integrate both sides.
28 through 30.
Choose 28 and 30. And then we're going to jump over and do a couple of evaluating ones. Well, maybe not. Maybe we might have to do more than one because each one of them looks totally different. All right, 34 through 40 even. You're going to do 4, just F of B minus F of A problems. And then there's some in here that are made to use the calculator, but I think I'm going to skip over those because you could just type them in the calculator and get the whole answer. So I don't see any reason to do those. So we're skipping to 48 and through 56 even, 48 through 56 even. And then I want you to do question number 62 and 64. And on 64, you might have to go and Google what inversely means if you don't remember what inversely proportional means. because that it tells it in words. It doesn't give the formula. It tells it in words, and you've got to figure out how to write the formula. But if you Google inversely proportional, you should be able to come up with a formula. It's a simple formula. All right. How are we coming on our graph? I mean, not graph, but quiz problems.
Worksheet. I'm struggling. I was trying to work on it, but
Let's see.
All right. Well, then I'm going to stop this video for Jacob and answer your questions if you have some.